All right, so we talked about how to construct the system of equations for implicit Euler method. But in this case, actually, the problem is easy because it turns out to be it's actually a linear problem. This is linear in y, and that's why at the end of the day, the system is going to be linear in y too. So we don't have any y squared, and x is always known because we know the x values for all points. And so we can convert this into a linear system down here, where I lump all the y's into a vector. This is going to be the coefficient matrix. And on the right side, I have the b vector for only the first equation. I have y1 because y1 is known, that's the boundary condition. And the right-hand side is 0 everywhere else. So you can go ahead and solve this linear system using backslash operator, and then you have the y values. So this time you see that to solve for unknowns, which are y's, we didn't use any iteration or any loop. We solved the linear system. That is the property of implicit methods. In implicit method, most likely you're not going to use iteration. Well, iteration over each equation. So all you have to do is you lump all the equations together like this, and then solve the system at once. There's no iteration over like multiple I values. All of I values, or different equations with different I values, all of them are lumped into the system. And we solve the system once. We don't solve equation by equation. And so if you look at the script, so the implicit method is right here. Okay, so I have the initialization for y, b, and then the coefficient vector, that's the coefficient matrix. And I construct the coefficient matrix using this, this part of the script. Well, there's a loop, but this loop has nothing to do with solving the equation. It's just to assembling the coefficient matrix, which is this matrix, right? Let's see how many points I have here. I have 20 points. So that means this matrix is going to be 19 by 19. So to construct this 19 by 19 matrix, I use the loop. So hopefully this is not confusing. The loop is not to iterate over each equation. It's just to construct row by row of this matrix. Okay, so back to the script. So I construct the diagonal elements here. I construct the b vector, the right-hand side here. And so this is the diagonal element. This is going to be the off-diagonal elements. Well, this includes actually the off, well, for I equal 1, that's the diagonal element. For all other i's, this is the whole row for the coefficient matrix. So as long as we have the a coefficient, you can go ahead and solve for the solution. So we go ahead and use backslash operator to solve for all the y values. And the rest is just to plot the function. I think this is it. So let me just stop the code here and run this implicit Euler method to solve dy over dx equals x squared times y. Anyways, so this is the solution. This is the y against the x. Okay, and we know that it's pretty much like an exponential function. But yeah, so again, here we didn't solve using, using any iteration over each equation. We solved the whole system at once using the backslash operator. Okay, so this implicit Euler method is also first order. So if we go back here, this is still first order, which means it's O delta x. The only problem, or maybe the only advantage is it's a stable method. However, the explicit forward Euler is unstable. So the only difference between explicit and implicit Euler is the stability, not the accuracy. The accuracy, both of them are first order. So we're going to talk about the stability after we talk about the next method, which is, well, maybe I can talk about the implicit, I can talk about the stability before I talk about the implicit trapezoidal method. Okay, so let me show you one code and clarify the stability in forward and implicit Euler. So let's say we want to solve the equation dy dx equals minus lambda times y. Okay, so dy dx, which is y prime, equals minus lambda times y. We know the solution to this is pretty much an exponential function which decays in x. Okay, so now we're going to start from lambda equal 1 and basically solve this using forward Euler. So this is forward Euler we had before. I just copied this part of the script right here using this f. Okay, so let's look at when lambda is 1. Okay, so that's pretty much right. It's an exponential function which is decaying. Now we're going to increase lambda. Well, just by changing lambda, nothing should change. I mean, this should still be a decreasing, exponential function. But let's see, because lambda is just a constant. So now I'm going to increase my lambda to 100. So this should really decay very fast, right? Okay, looks like what's okay. So initially is 1. And it goes down very quickly to 0. Well, this is going really fast, so that's why you don't see more steps between 1 and 0 here. But anyways, it's going down, so it's not too bad. Let's increase lambda to 200. So this should be decaying even much faster. Now you see that actually it's increasing, and it goes up and down. So, well, now part of it actually is decaying, part of it is increasing, and this part which is decaying is negative, which is completely wrong. I mean, the solution should be always positive because the exponential of any number is always positive. And so you see that part of the solution is negative, part of it positive, and the positive range, the positive value is actually increasing. So it's completely wrong. I didn't change anything except lambda. So that's what we called unstable. For some lambda, we got this thing very accurate. I mean, decreasing function, at least it was looking fine. But as soon as you change lambda to some large number, the same method, the same solution, the same delta x leads to a very weird result, which is completely incorrect. So we call the method is unstable. It has nothing to do with delta x. The method, the way we discretize it, is unstable for some constants, for some values, a combination of the constants and delta x. Okay, so this is the property of explicit methods. Implicit methods do not have this behavior, or do not show this behavior. Okay, that's why we always go with implicit methods, if possible. Because we want to avoid this weird behavior that is not predictable. Now, in this case, we know the exact solution. If we do not really know the exact solution, then it's really difficult to figure out whether this is due to instability, or due to something else. Okay? So, just to keep in mind and basically clarify this, hopefully clarifies what the difference is between stability and accuracy. Okay, so the method was accurate for some lambda and it's completely inaccurate for other lambdas. Okay, so this leads to basically, or this is caused by the stability issue. Okay, so let's move on to now the next implicit method. We said implicit Euler method is first order, is O delta x. Now we can increase the accuracy of it and make a method which is O delta x squared, and that is implicit trapezoidal method. Okay, it's also called Adams-Moulton. Adams-Moulton method, the same as implicit trapezoidal method. The way we solve this problem, our differential equation is we discretize pretty much like the implicit Euler method with y plus 1 minus y divided by del x. That's to discretize dy dx. However, if you just actually look at implicit Euler right here, so you see the left side is the same, but now the right side, in implicit Euler we had xi plus 1 yi plus 1. In Adams-Moulton, or implicit trapezoidal method, we have the average of xi yi and xi plus 1 y plus 1. So this is pretty much like a trapezoid. One side of it is fi and yi, f of xi yi. The other side is f of xi plus 1 yi plus 1. We get the average of the two times del x. If you think of del x as the height of the trapezoid, this basically gives us the area of the trapezoid. So that means we are basically integrating a function, calculating the area under the curve using the trapezoid area. Okay? And that's where the trapezoidal method comes from. Okay, so now this is still implicit because yi shows right here and here. It's not explicit, okay? Now yi plus 1 is unknown, so we have to move it all to the left side. Okay? So the proof that why this is second order actually is down here. I'm not going to cover it, but for you, I think this is a good read. Go ahead and see how I proved the accuracy of trapezoidal method to be the second order. Okay, so now we have to move I plus 1, all the I plus 1 to the left side and all the i's to the right side and solve the system for different I values, given that any y is going to be unknown now. Okay, because let's say we only know y1 there in the first point. We don't know y2, and we know that y2 is related to y3 through the second equation, so we don't know y3. y3 is related to y4, so we don't know y4, we don't know y5, we don't know all the y's all the way to the end except the first y value. Okay, so that leads to a system, and we have to go and solve it. But this time, let's look at this problem. This time actually the problem is nonlinear. Let me see, is this non-linear? Well, actually this is still linear. So this is still a linear problem. We can easily go ahead and use backslash operator to solve it. But you can imagine that if f, which is the right hand side of the equation, is nonlinear in y, then the method could be completely nonlinear. The system could be completely nonlinear, and you have to use nonlinear solver to solve it. Okay, so let's go back to this equation. Let's say we want to solve this differential equation. Same thing we did with implicit Euler method. Okay, so on the left side we have y plus 1 minus y divided by del x, which is the discretization of dy dx. And on the right side I have the average of the I value and then I plus 1 value. Okay, so we have to move all the yi plus 1 to the left side and keep all the yi to the right side. And factor out y plus 1 and then crank up I from 1 to all the way to the n minus 1. Now by doing so we get this system. So in the next video I'll show you how to solve the system, again using backslash operator, and part of the script actually does this. So stay tuned for the next video, and thanks a lot for watching.